Welcome to Unit 9, Lesson 2, Transformations of Logarithmic Functions. Just like in every other unit that we're dealing with graphing, we are going to have those transformations that can happen to our graphs with the values a, b, h, and k. So just as another reminder, a and k affect the y values. A is a vertical stretch, k is a vertical shift, and then b and h affect our x values. B is a horizontal stretch, and H is a horizontal shift. This table here shows what happens to your mapping points. This is not new information. You are very familiar with this already, but just as a reminder, when we have A, if you have your mapping points, it multiplies the y values by A. B, whatever the B value is, you're dividing X values by it. H is a horizontal shift. It affects the x values, and then k affects the y values. So just keep that in mind as you're going through this part of the unit. The function will look like this: y is equal to a log c b x minus h plus k. So nothing's really changed. The only thing that's new here is the log c. First, we'll look at the translations of a logarithmic function. So you use transformations to sketch the graph of the function y is equal to log 3 x plus 9 plus 2. You want to look for your base here and think about, what is my base function? My base function is 3 to the power of x. So y is equal to 3 to the power of x. You have those mapping points. You can just plug them in, put an x value there, see what y equals. So 3 to the power of 1 and 0, 1, 3 to the power of, excuse me, this should be using this table, comparing y is equal to 3 to the power of x and y is equal to log 3x. Remember, these are reciprocal functions. This one is not graphed on this graph. It's just there to give you the values to graph this one, y equals log 3x. I apologize, I made a little mistake. I mixed up the coordinates. So this, of course, should be 3 to the power of 0, gives us a y value of 1. So just flip that and then flip it in the log function as well. So you should have 0, 1, and 1, 0. So all you do to get your values for your log function is use these mapping points from your y is equal to 3 to the power of x and just swap the x and y. Once you have this base function, y is equal log 3x, you can use the table on this side and think about what happens to the x and y values. Now, we don't have any vertical or horizontal stretches here. We just have a horizontal and vertical shift. So what we're going to look at is x values minus 9 and y values plus 2. So up to over 9, up to over 9 to the left. This should look really familiar to you. It shouldn't be uncomfortable to figure out how that graph is moving. Below this, we have some explanation about some variables on the graph of the transformation. So we're using this one that shifted over to x equals negative 9. So the asymptote, x equals negative 9. Our domain, it's going to be x is greater than negative 9, and then true for all other x values. Y is negative infinity to positive infinity. The y-intercept, if it exists, it does. It goes through 0, 4. You can read that right off your graph. If you didn't have the graph, you could always just plug 0 for x into your equation and see what you get. The x-intercept in this situation gives you a fraction, so you're going to plug 0 in for y and then solve for that value of x. All you need to do is follow BEDMAS. So step number 1, you're going to move the 2 to the other side. You'll have negative 2 is equal to log 3x plus 9. Now treat this as brackets. This is your answer. This is your base. This is your exponent. Base, exponent, answer. Now we have 3 to the power of negative 2 is equal to x plus 9. 3 to the power of 2 gives us 1 over 9 equals x plus 9. And then I would convert this into a fraction just to deal with it more simply. Remember, 9 whole pies would be 81 pieces of pie. divided into 9 separate pies. So 81 over 9 becomes that value. These are equivalent. And then you just subtract 81 over 9 from both sides. And you can leave it in this form, negative 80 over 9. That's a perfectly acceptable answer. Just remember base, answer, exponent, and change it to exponential form and then solve for x. That's the easiest way to do it. In the next part, B, reflections, stretches, and translations of log functions. We now have a horizontal stretch as well as a horizontal shift. So you have your mapping points, x, y, and of course, based on this logarithmic function, our b value is here, and our h value is here. This table deals with it in 2 separate steps. So we would be starting with y is equal to 2 to the power of x, and then changing that to logarithmic form. This would be your b transformation, and then this is your horizontal shift, moving it over. So 0.5 minus 3. So here we've taken all the x values and divided them by 2. And then the next step is to subtract 3 from all the x values to move it over 3 steps. So there's a bit of information missing here, but you can know it by all your previous knowledge about this. We're going from y is equal to 2 to the power of x, and then y is equal to log 2x. Those are the first 2 base functions. They're inverses of each other. And then we're applying that b value and that h value. So we have the determinant, the equation of the asymptote, x equals negative 3. It will never touch that line. The domain, x is greater than negative 3. Y, again, it's not giving us a perfect value here. You could leave it as an answer like that, or you can approximate it if you need to. And then the x-intercept, it's going through nice and clean through that point, negative 2.5, 0. So you just read that right off your graph. Of course, like many of the other units, you're going to want to be able to determine the equation of a log function given its graph. So the top graph and the bottom graph, in the textbook, it's red and blue, but the top graph and bottom graph is how we'll refer to it. So it can be generated by stretching the graph of y equals log 4x. So here's our base function, log 4x, and then we're going to do a stretch to it. So note the translation has undergone a horizontal stretch since a vertical stretch does not change the x-intercept. So method 1, compare the graph of y equals log 4x. So the key point for 1 on the graph, that's this one right here. We want to see how far has it moved. So in the original graph, we have a point at 4, 1, and in the transform graph, we have our point at 1, 1. If you remember back to the first unit, the translation can be created by horizontally stretching the graph, y equals log 4x, about the y-axis by a factor of 1/4. This is 4 times less than the original function. And you can get that value just by looking at the difference in them. So the translation can be described as the equation y equals log 4x, where the b value is, of course, the bottom of this fraction right here. There's also a method 2 for this, so you just pick which one works for you and do that. Method 2 is use points and substitution. So the equation of the translated graph is of the form y equals log 4bx. Substitute the coordinates of a point on the translated graph, such as 4, 2, into the equation and solve for b. So you can just do it algebraically instead. We don't know b. B times x is times multiply, so we can just switch the values around so that it becomes a little bit easier to isolate that variable. So we have y is equal to log 4bx, and 2 is equal to log 4b. 2 and 4 right here just came from the graph of the transform function. Then we get the base 4, the exponent squared is equal to 4 times b, and then you're just solving for b. This would be 4 squared, which is 16, divided by 4 will give you b. Beyond that, you have some practice questions and you can complete those before class.